Hi everyone, I'm Aspen. I'm staff ML engineer at VirtusLab. And tonight I'd like to share with you some of my experiences generating embeddings at scale, hence the title. So my motivation for this talk was I was tasked with creating a semantic search system for quite a big data set. Initially, POC was 50 million records, company descriptions, and beyond the example that you see below, this is coming from Llama Index documentation. There were non-examples how to run embeddings at scale. So usually it was for document in the corpus, embed document, and this doesn't work for 50 million documents. The second motivation is the importance of embeddings in RAG applications, and maybe a little survey. How many of you know what RAG is? Okay, so less than a half. So RAG stands for Retrieval-Augmented Generation. This is a technique that gained traction recently due to the popularity of LLMs. And the way it works is that we have an external system of knowledge, and we pull data from the system to enrich the knowledge of the LLM and provide context for it to answer. It also reduces hallucinations and allows us to utilize proprietary data that's otherwise not available in the generally available models. Yeah, on the right is the same code that is also doing embeddings, but as you can see, there is a lot more to it than just get text embeddings, and I'll get to it in a second. So we're going to go through embeddings 101 to explain what embeddings are in general, the pipeline overview for generating embeddings at scale, the importance of understanding your data, which drives the model selection, a little bit about vector databases. They are not really crucial for this talk because we're focusing on the embedding generations at scale, and also some optimization techniques and tips. So there are two main ways to represent text by machines, and one of them is sparse encoding. And sparse encoding, you can imagine that you have all the words in the corpus, and the corpus is all of your text. So you have like a large Excel sheet, and in the columns you have all of the words, and the rows are your documents. And wherever you have a word in a document, you put 1. If you don't have that word, you put 0. So it's sparse because most of the entries are 0 in this document, whereas the dense representation is lower dimension. And it's not as clear as sparse representation. This is calculated by neural network. So each of these dimensions represents some semantic feature, and the larger their dimension, the more semantic features it can represent. So BERT models were first to represent text in a semantic way. BERT models represented all of the words separately. So there was a vector for each of the words. And sentence transformers added a layer on top of it that made the whole text a one a vector. So this gives us comparable, because if we have a vector per word, then it's very hard to compare texts of different length. And if we have one vector with the same dimension, it's comparable, hence we can do search and other operations. So this is when synthesis transformers came in. And the difference between embedding models and LLMs is that embedding models focus on representing the meaning of the text. So the result is sort of a meaning. It's vague. It's not really that interpretable. There are methods, but this is not a talk about it. Whereas LLMs generate also vectors, but these vectors tell us what the next word should be. And embedding models tell us the meaning of the sentence. So how do embeddings fit in the context of RAG applications? As you can see, here we have an orchestration. This is something like LangChain or Llama index system. User is posting a query to the front-end app. It goes to the orchestration. Then through the embedding model, we get embedding of the user query. And we pass that query to the vector database, which returns us the similar entries to the user query. And using the LLMs, we compose answer that goes back to the user. What I'll be focusing on is the top part, which is the pipeline, embedding models, and getting those embeddings into the vector database. So this is an overview of the pipeline. We have our database with data that we want to process, documents, and these go into embedding generation pipeline. Let's skip the delete part for now. We process the corpus. The processing means turning each of the text into document, and each document is turned into node, because embedding models have a limit of the number of tokens they can represent. We need to do something called chunking, and the nodes are the chunks of the documents. And then we embed these chunks or nodes. We get embeddings and we insert them into a vector database. The pipeline below is another important component. So if our data is changing, then we need to have a system that updates our embeddings in the vector database. So the way it works, we have a data update that goes into database, and this update is publishing a message to the messaging service that there was an update of the data, and then we trigger update of the entry in the vector database. And it could be an update or it could be a delete, hence this delete part here. So before we choose the model for embeddings, we need to have a little bit of understanding of our data. And the most important part is how long our texts are and what the texts are about. So there are simple techniques that we can use to assess how long our texts are. One of these techniques is to just take the number of words for each of our documents and then multiply it by 1.3. This gives us roughly the number of tokens. But if we want to have more detailed and accurate measurement of that, we can sample the documents and tokenize them using our model of choice and get the number of tokens. So choosing a model is best done by looking at the most popular benchmark for text embeddings, which is called MTEP. And you can see this leaderboard here. We have a name of the model, model size, which drives the how much memory is required for the model to run. The embedding dimensions, the more dimensions, of course, the more semantic details are encoded by the model, max number of tokens, and also the scores across different categories. And also on the top, you can see different tabs like classification, clustering, re-ranking, retrieval, summarization. So this is important because we need to choose a model that fits our application. So don't only look at the overall scores, look at the tabs that connected to your application. So with the model selection, there is a question, why not use the embeddings from OpenAI? It's faster, it's easier. But open-weight models are cost-effective, and probably the most important part is that they are customizable. So we can take a model, and if the distribution of the data that the model was trained on is different than the distribution of our data, we can fine-tune the model so it works better with our data. And this is something that we cannot do with the models that are externally hosted. Okay, so when you have MTAP and we go into one of these models, there are things worth looking at. And some of these things are like, is there a paper available? If there is a paper, then probably there is some information about the data it was trained on. This gives us information about the distribution of the data that the model was trained on, and we can match it to our data. There's some information around training process. Usually it tells us how many tokens we can use. Downloads seems trivial, but the more downloads, the more users, the more the community there is around the model. Very important. License, also important in corporate environments. We can also look at fine-tunes and quantizations. So quantizations reduce the number of bits the model is using to represent the weights, and hence reduces costs and improves the performance. And here we can see that if we go to Files and Versions tab, we can see that we have fine-tunes of a model. And also there are tips to improve performance as well. So it's worth looking at the model cards. I think I mentioned everything here. All right. So this is a sample comparison of the cost. I know everyone cares about it. So the scenario is 50 million documents. This is the scenario I was working on recently for the POC. 50 million documents with 20 words. This is average number of words in an English sentence. This is around 26 tokens. So it means 1.3 billion tokens total. And the pricing for the best OpenAI embedding model, which ranks 30 in MTAP, is 0.13 per 1 million tokens. So if we multiply it, we get $170 to embed these 50 million documents. And this is the pricing for the solution that I used, 4 times NVIDIA T4 GPU, using the GTE large model that I also showed screens from before. ranks 25, and the cost is $33. It took 24 hours though. Just a very quick note on vector databases. There are mistakes that can happen during creating indices in the vector databases that I learned the hard way. So, for example, Llama index is creating random UIDs for each of the records in the vector database in the index. So if you don't have a supplementary database that is matching your data to these IDs, then you're screwed because you cannot update it basically. It's random ID and you cannot go back to the data. Sparse vector support, we're not going into this. This is like a topic for another presentation. But combining dense and sparse representations for lexical or hybrid search usually yields better results. Databases also can store metadata, which can be useful for filtering out during the semantic search. And also pay attention to similarity functions that VectorDB supports. So each of the embedding models is trained using specific similarity function. So you need to make sure that the vector database that you're using supports the same similarity function. Usually it's cosine, and every database supports cosine. But if you use some niche model that uses a different function, that might be problematic. Okay, so now we're going into the most interesting part, which is a generation of embeddings. So the process is to start simple and implement generation of embeddings for a single node and single GPU. So we've got our data to process. This is our embedding worker on a single node with just one GPU. And we start with reading the X longest text from the source to estimate the batch size. And we read the longest text from our corpus because the memory consumption of the model depends on the length of the text. So if we just read random data, it means that probably the memory utilization will be lower than the average, the maximum utilization of the memory. So we pass this estimate into our worker loop, and here we operate on 3 different processes and 3 different queues to optimize the whole process. So there's a process data queue, the embeddings queue, and the upserted queue. So we read batch of the data, we push it to the queue, and embedding process reads from the queue and generates embeddings, which are pushed to the embeddings queue, and the upserting process is pushing the data to the vector database, but also to the upserted queue, which saves a state of the process in our helper database. So if something goes wrong, we can resume the process from the point where we last finished. Important thing here is to catch the out-of-memory errors, which can happen even with the right batch size, and implementing retries for upserting into database and probably also for the reading of the data. Okay, now we add more GPUs to our one node setup. And basically, we can reuse the worker code for a single GPU and spawn multiple processes for each GPU and load the model on each GPU. This is sort of similar to DTP in PyTorch. The difference is that there is no training, so we don't have to gather gradients. So we don't really need DTP. We can use just multiprocessing to spawn process on each GPU, load the model, and each of these workers. So this is the same as the whole diagram before, but now we have it for each of the GPUs. And our main process prepares splits, spawns the workers, but also creates a shared dict and barriers, because we need to estimate the batch size, and we also need to create index if it's not present. So this is only happening on rank 0 to avoid any race conditions. And this is communicated after batch size is estimated. This is communicated through the shared dict and the use of barriers to other workers to synchronize the start of the embedding process. Yeah, and we still use, of course, the vector database and helper database to store the state for each of the GPUs. So in terms of monitoring, we can use, of course, NVIDIA SMI and check the usage of the GPUs. And here is a common problem. If you use threading instead of multiprocessing, then there will be gaps in GPU utilization. Because whenever the data is processed, it cannot embed. So it's important to use multiprocessing, not threading, to make sure that GPUs are loaded 100% all of the time. So such use of GPU is a sign that the data processing is slower than the embedding, and you need to change the batch size for the data processing, for example. So now we have multiple embedding nodes. This is a much more complicated setup. Now we need an orchestrator that spawns nodes, and each of these nodes have their own GPUs. And the simplest implementations for that are torch distributed. But you need to manually start those X nodes with X GPUs and run torch run or torch distributed to synchronize, which is laborious. Slarm plus torch distributed, if you have experience with HPC clusters, this is quite a good setup. But in my opinion, the perfect application for this is Ray, which is a framework or cluster for distributed Python applications. And it's very easy to set up and supports communication between the nodes and the workers out of the box. And I think Ray is the best application for such scenario. So some optimization tips. You can use 16-bit precision to use memory usage, to reduce memory usage and increase throughput. Just make sure that your GPU allows for that, because not all of the GPUs support lower precisions. Make sure that all of the types that are coming from the embedding model, from your orchestration framework, or your vector database are using the same types, because the conversions between NumPy, floats, or other representations of the numbers can cause differences in similarity metric calculation. Quantized models are quite popular in the LLM world, but in the embeddings world, there is a limited availability of pre-quantized models. You can do it, of course, yourself, but you need to rerun the benchmarks like MTEP to ensure that performance isn't degraded. The better technique in embeddings world is to use Matryoshka representation learning, which reduces embedding dimensions while retaining the performance. Better alternative to quantization. And also, you can choose many different dimensions lower than the original dimension. Still need to run benchmarks though, remember. Yep, that's it from me. Questions, comments, experiences, welcome. Thank you.
So, suddenly, you mentioned that this was the part that our teams most of them, right?
Yes. Yeah.
This you will see has it been already made? Did it make the production?
Yeah, actually, it make to production in 2 months since I joined the company. It was my first project actually in that company, and it was a great success. Yeah.
So it did make production 2 months ago, right? That's what you're saying. Already it will be production.
No, I started the project 2 months ago, and it's going into production right now. Yeah.
Right now.
Yeah.
So maybe you have a question.
Okay.
Yeah, I have a question about interchangeability of these embeddings. So how it looks like, because we have different approaches, and just in some perfect world, it's possible to use some cheapest model to make embeddings and use it, for example, for ChatGPT. So it uses.
What is the question?
Question. So is it possible at all? To use some cheap model, get embeddings, and then use these embeddings, for example, for some cloud-based or some more expensive model without doing so.
So, of course, the lower the dimension, the smaller representation space of semantic meaning there is. And of course, the shorter the sentences, I would say, work better with lower dimensions. But if we want to embed long texts with very low dimensions, that's not called well, I think, yeah. But yeah, of course, it's worth experimenting with. And I think what I didn't mention here is the importance of performing evaluations. Evaluations are hard because you need to create your own gold standard data set. So you have a query, you embed it, and you query the vector database, and it gives you results. So how do you evaluate whether it's good or not? So you need humans to label the data as a good or bad result. So it still takes manual labor. So that's how you compare models, basically, and results between them.
Do you have any more questions?
Hi there. You mentioned that you built this system in order to supplement the RAG, right? So the typical scenario would be user puts a query and system goes into production. The query goes through some kind of deployment of the embedding system, and then you get from the vector database some supplementary or contextual information in order to answer the user query using some kind of LLM. My question is, because you mentioned that basically the setup for preparing the data into the database, what about the situation when you have online system, and how would deployment of those embedding models would be in a live system? How would it look like?
Okay, so we have basically REST endpoint, which is during, so I'm using Fast API. In the newest versions of Fast API, you have a thing called lifespan. It's a function that is executed at the beginning and the end of basically lifespan of the application. And at this point, you load the model and save it in a state of the app. So it's available with every request. So when the request comes, you are able to embed the user query and then pass it on to the vector database and pass the results to the LLM. Of course, if you have, the setup can get complicated. So if you want to host an LLM on the same machine to reduce the latency, then you need two GPUs, one for the embedding model, the second one for the LLM. But yeah, basically that's how it works. Yeah.